Now, I would like to introduce you to a very exciting speaker for our next keynote that's starting now. So, our speaker is Professor Peter Corke from the Queensland University of Technology. He's going to be talking to us this afternoon about creating robots that see. So, Professor Peter Corke, he's a robotics research and educator. He is the Distinguished Professor of Robotic Vision at the Queensland University of Technology and the Director of the ARC Center for Excellence for Robotic Vision and Chief Scientist at Dorabot. His research is concerned with enabling robots to see and the application of robots to mining, agriculture, and environmental monitoring. He created widely used open source software for teaching and research, wrote the best-selling textbook, Robotic Vision Control, created several MOOCs and the Robot Academy, and has won national and international recognition for teaching, including the 2017 Australian University Teacher of the Year. Peter Corke is a fellow of the IEEE, the Australian Academy of Technology and Engineering, the Australian Academy of Science, founding editor of the Journal of Field Robotics, founding multimedia editor of the International Journal of Robotics Research. He's a member of the editorial advisory board of the Springer Tracts on Advanced Robotics series, former editor-in-chief of the IEEE Robotics and Automation magazine, and a member of the executive editorial board of the International Journal of Robotics Research. And in addition to that, Professor Peter Corke is the recipient of the Qantas, Rolls-Royce, and Australian Engineering Excellence Awards. He's held visiting positions at Oxford, University of Illinois, Carnegie-Mellon University, and University of Pennsylvania. He received his undergraduate and master's degrees in electrical engineering and PhD from the University of Melbourne in Victoria. So it's an amazing opportunity for us to have Professor Peter Corke talking to us today. We'd like to welcome him to our virtual stage. Thank you very much, Peter.
Mute myself. All right. Is the technology working? Can you hear me?
Yes, we can hear you.
Perfect. Alrighty, Paolo, thank you very much for the kind introduction, and it's a pleasure to be talking at Acre, even if it is a virtual one. What I'd like to do today is talk around a bunch of issues that are interesting to me about the intersection, the overlap, if you like, of robotics and computer vision. I guess I've had my foot in each camp for a long time, and I've got some perspectives about the different ways roboticists and computer vision people go about their research. So that's what I'd like to talk about today. This is a PDF of the slides on that shortened URL if people would like to quickly take note of that, because I'm going to change slides. All right. So robots, as you would all know, are very mature technology today. Modern robots are fast, accurate, strong, and relentless. First robots that were built and went to work for humans were ARM-type robots that really found their form and their niche in manufacturing. And in probably in the last decade, we've seen an explosion in interest in mobile robotics. And I have to say, I think Amazon have aced this. The fleet of, I understand now, well over 200,000 robots in operation, which make Amazon essentially a robot-enabled business. They couldn't be what they are without robots. And of course, all the AI technology, cloud, and so on as well. So that's where we are with these robots, but their perceptual ability is really very, very limited. And we also know that robots have got quite low uptake in many, many industries. So yes, they might be dominant in manufacturing, they may be dominant in fulfillment centers, but we don't see very much of them in mining. Yes, there are haul trucks, autonomous drill rigs, underground haulage, but there's lots of other jobs on a mine site are not automated at this point. Construction is still incredibly labor intensive, as is agriculture, small scale manufacturing, and then big expensive things for society like healthcare, hospitals got a very, very low rate of automation. And I'm not just talking about the sexy stuff like surgery, robotics automation is making some inroads there, but it's all the material transfer within a hospital, linen, drugs, samples, specimens going hither and thither, all mostly pushed around or carried around by humans. So you got to ask the question, why is this? My very firm belief is because robots don't have the perceptual ability at the moment to understand the world around them, which we accept. We thrive in these kind of environments, but they are chaotic, they're dynamic, and robots at the moment just are not up to that. It's the perceptual limitation that they all have. And of course, we dream of other sorts of robots, and we just don't see any robots like this around, right? We just don't see them. What's interesting to me is that really for the longest time, robotics has been considered very much as a problem in geometry. The idea is that if we can make a geometric model of the world, we can solve problems like navigation and manipulation purely in terms of the geometry. So a lot of effort in robotics has been expended in trying to do geometric reasoning and to acquire accurate geometric models of the world to allow that geometric reasoning to take place. Now, geometric reasoning really requires very, very high precision of the geometric entities you're going to reason over. And that poses a problem on the perception side, because to get sufficiently accurate geometry from real-world sensors remains a very big challenge. And I'd also argue that geometry is really not enough for a lot of tasks. So I'll give a few examples here. The traffic light, I can use a geometric sensor. I can get a point cloud and I can recognize a traffic light, but I can't tell what color the traffic light is. And the same with a car. I could process the point cloud and make a decision that there was a car there, that cloud of points was a car, but I can't tell the state of the brake lights. And similarly for a human face, maybe I can recognize a human, that it's a person, but to recognize who it was from the face, to understand their emotional condition from their facial expression or what direction they're gazing in is almost impossible from the sorts of point clouds we can gather by robots. So if you consider a bunch of things that human beings are very good at, and I'll just give a few examples here. There's a girl on the left solving a Rubik's Cube, and so she's using her visual sense to build an internal representation of the cube in her mind, and she can reason over that and then actuate her fingers to solve the cube. The driver at the top, crazy driver at the top, is really a visual processing system, right? They're taking information through their eyes, basically two cameras, processing it, and then using that to control their hands and their feet to drive the vehicle. So this really is an exercise in visual perception and visual processing. The whole task is completely mediated by vision. And humans can do this pretty effortlessly, but this is still a challenge for robots today. And down the bottom, we have people juggling. Again, that's a very visual task. But it's not simply enough to understand where things are in the world. We need to know where things are in the future. We need to do visual prediction. And that's a really core part of our visual system, is that we can predict what the short-term future will look like. And I guess we've evolved that because it's got a huge evolutionary advantage. What's interesting compared to the robotics approach, which is geometry heavy, is that in none of these tasks are we building three-dimensional representations or geometric representations of the world, right? We're not doing pose reconstruction. We're not doing shape reconstruction. It's all concerned with relative position and relative velocity. And we sense those things very, very well. But robots don't do that. And I think maybe there are some tricks there that we could perhaps apply to build better robots. Another example is threading a needle. Most of us can thread a needle fairly well. It's not about estimating the three-dimensional position of the end of the cotton in the world coordinate frame or that of the hole. It's simply a matter of making those two things coincident. And that's an easy thing for us to do. Doesn't involve any geometry at all. So the sense of vision is fascinating. Life on Earth has been around for 4 million years. Life appeared almost instantly after the planet was formed. It was very boring for about 3.5 million years. And then 540 million years ago, there was a genetic mutation turned a chemical receptor on a cell into a photosensitive receptor. And the sense of vision was born at that point. And we still have that genetic mutation in the cells in the retina of our eyes. So a very important genetic accident. And it really then unleashed a whole bunch of very, very interesting life forms on Earth from that point. And there is a theory, the so-called light switch theory, that said that it was one organism having the sense of vision kind of set off an evolutionary arms race that led to the complexity of life that we see today. So the sense of vision has perhaps had a very profound impact on life on this planet. So that's the Cambrian explosion, as we call it, 540 million years ago. And today there are about 10 different eye designs that exist in nature, based on a number of very different principles. Some of them are literally a pinhole lens. Some of them are like small reflector telescopes. Some have got the light sensors on the top of the retina, some on the bottom of the retina. So evolution has explored the design space of eyes and found the number of solutions that are sufficient for the organisms that have them. And all organisms that don't live in dark places have eyes. The only creatures without eyes are those that live in places with no light, where it confers absolutely no advantage. The other thing that interests me a lot about the sense of vision is that it scales. So you consider a very simple creature like a bee. A bee can learn the location of a flower, of food, from another bee. A bee does a dance, the other bees understand the dance, and then they set off in a particular bearing angle with respect to the sun and a particular distance. And they measure the bearing angle and the distance that they've traveled using vision. They can land on a moving flower. They can gather the nectar and the pollen, and then they can return to the hive, again using visual navigation. And all of this is with a brain that weighs a gram and contains just 1 million neurons. That's a staggering achievement. So I have total respect for the visual capability of very small creatures. We're creatures with very big brains. Human brains about 1.5 kilos, 10 to the 11 neurons, and a third of that is devoted to visual processing. It's the back third of your brain does that work for us. A couple of other interesting things I want to share with you about vision. The human visual system is complicated in many, many ways. And one of the ways is that we don't just grab a snapshot of the scene through our eyes and process it with some algorithm and come up with a result. That's the very sort of reductionist thing we do in computer vision. Take a picture, run it through an algorithm, and then sift through the results that come out the end to get what we want. We have active vision, and so our eyes are continually moving over the scene. Our eyes are driven by the highest performance muscles in our body, huge rotational speed and acceleration capability. And the way they move depends on the task at hand. And so you can take experimental subjects, you can put a picture in front of them and ask them questions and track their gaze. And their gaze moves over the picture in a way that depends on the question that you ask them. So in this particular case, the subject was asked about the material circumstances of the family. And what you can see is that the person's gaze is checking out the quality of the possessions in the house. They're checking out the furniture, the paintings on the wall, maybe looking for jewelry around the woman's neck, and so on. But if you ask them a different question, you get a very different trajectory. So we acquire the information we need for the task rather than requiring all the information from the scene and then sifting through it. So this has clearly got a computational advantage. It's probably got an energy advantage. And perhaps it's a trick that we will build into future visual robot systems. The other thing that I find very interesting about the visual system is that we've got about 1 million neurons come from our eye back to a structure at the bottom of our brain called the LGN, which then feeds into V1, first part of our visual cortex. But interestingly, there's a huge number of pathways from V1 back to the LGN. So it's not a left to right pathway as we often create in engineered visual systems. There is this interesting feed forward, and there's lots of speculation about what that's for, what it does, but it's interesting that we have this particular architecture. And the big challenge for us as engineers is to build a vision system that's as capable as we are, one day better than we are, but that can do so with so little power. And so our visual cortex probably consumes about 6 watts of power, and that's so far away from where we are with GPU clusters today. That's absolutely an aspirational goal for those of us concerned with algorithms for processing images. So, in summary, I would argue that vision's our most powerful sensor. It's critical to everything we do every single day, and not having vision is a very profound disability for human beings. And robots share that same disability. They really don't have the ability to see. They miss out on all the information about what's going on around them. And there's a bunch of reasons why vision is hard for robots. I'm going to go quickly through a few of them. One is that there is this ambiguity between appearance and geometry. We can be tricked by things that appear to be a geometric structure, and actually they're just appearance. So these are artistic impressions of bridges in the distance or holes in the sidewalk that really aren't there. They're just optical illusions. And so we want a robot to not be fooled by a picture of a door compared to an actual door. This is important competence that a robot should have. Humans use a lot of tricks to estimate distance in the world to try and break this ambiguity between geometry and appearance. So we use Binocular Stereo, and this is a very well-known approach to many roboticists and computer vision people. Computational stereo is a big thing in our field. We use information from the muscles that control the lens in our eye. We use information from the muscles that control the divergence of our eyes. We use information from motion. We use information from occlusion, the apparent height. If I know the size of a tree, then its apparent height on my retina gives me some clue about how far away it is. Texture density and aerial perspective. So our brains fuse all of these visual cues together to give us pretty robust estimates of how far away things are and how quickly they're moving. Now, computer graphics is a relatively old and mature field now. And computer graphics says that if I've got a model of everything in the scene, then I can synthesize the image. So the image is a function, complex function, but one that we can compute very, very quickly today, of the scene geometry, the materials that comprise the scene, our viewpoint, the lighting conditions, and atmospheric conditions like smoke, fog, rain, and random other stuff. So if we know everything about the scene, we can synthesize an image. But in computer vision, what we want to do is almost the inverse of this, right? Given an image, we want to learn what's the shape of the scene, what's it made of, and where am I standing with respect to the scene. Now, this function, curly p, that I put here, is essentially not invertible. So we can't do this very simply. There's just too many solutions. And to solve this, we need to bring in some extra information. We need some constraints to pin down the geometry, materials, and viewpoint we want to solve for. So these are assumptions, information from other sensors. It could be information from the context, or it could be from our experience. And my hunch, and it's only a hunch, is that the reason that deep networks are able to do as well as they do is that by processing, looking at so many images of the real world, that they've kind of built some implicit model of these assumptions. They've got some idea of how the world works, what's a valid scene and what's not a valid scene. Now, it's not explicit in most of the neural networks that we see in computer vision, but I imagine that it's somewhere implicit in all of those weights. And I think that's why they have such advantage over more traditional approaches. Now, humans deal very well with ambiguity, and here are three that I find amusing. Initially, when we look at it, we get surprised, and our rational brain kicks in, and we say, okay, there are no such things as small people. It must be a trick. And then we reason about the trick, and we figure out what's going on in all of these cases. The person is on my fingertip is standing further away. The furniture is stupidly big, or the people on the right are moving in a room that's built very, very strangely. So another reason the vision's hard for robots is because appearance is not necessarily the same as location. In robotics, mobile robotics, we care a lot about location. Where am I is a famous question in mobile robotics, right? And we can be at the same place and its appearance can change, and we can't conflate those two things. So each column here represents the same place, and the variation in the first column is that the time of day has changed and the atmospheric conditions change. It's the same place, but it just looks radically different. And just by naively processing patterns of pixels, you're not going to pick it's the same place. The middle column is just simply a change in lighting conditions. The top one is an overcast day with no shadows. The bottom one is a sunny day with lots of shadows. And sadly, a lot of vision algorithms get very excited about shadows because they've got sharp edges and lots of corners. And they're not real. The shadow is not a real thing. It's just a pattern of lighting projected onto an underlying surface. Number three is an interesting one. What's happened? It's snowed. So you could argue that this place is now made of different stuff. In the bottom, it's made of gravel and metal. In the top one, it's made of frozen water. But it's the same place. Its appearance is different because it's actually covered with a layer of very different material. And we might see that in urban scenes. It might be at some times of the year the ground is covered in dead leaves, or the grass has changed from green to brown, or the trees have lost their leaves. So this is a very real problem in robots trying to understand the world, knowing that its appearance changes even though the places have not structurally changed. Another couple of examples here showing very big differences in appearance based on time of day and viewpoint. And of course, vision's hard because of the difference in viewpoint and the very rich variation in the appearance of objects that belong to the same class. Here are objects belonging to the class cup. And this is a problem deep networks have solved to a large extent, but definitely an issue. So if we look at what the computer vision people have been doing for the last few decades, they've made some very impressive strides. And if you visit any of the major computer vision conferences, read the papers, look at the videos they produce, progress in computer vision seems to me to be much faster than the progress in robotics. And as a roboticist first, this kind of frustrates me, but I think, well, there must be something that we can learn from what the computer vision people are doing. And I want to touch on some of those. So examples of captioning. Now, the network doesn't understand what's going on in the picture, but networks can generate pretty decent captions for images, and that's advantageous because the captions maybe got 20 bytes or 50 bytes, compared to 10 megabytes that might be in the original image. So that's powerful data reduction. It's getting to the essence of what's in the picture, and to me, this is very impressive. Networks can do things like imagine the skeletons of human beings, which is useful to understand how people are standing. We can estimate age and gender. Very interestingly, for robotics, we can do good semantic segmentation these days. And it's far more useful for a robot to know that a pixel corresponds to ground or a tree or a car or a person than it is to know that a pixel comprises this much red, green, and blue. The semantic information is very, very rich, very, very useful for robotics. And there are networks now that you can show them an object and it will tell you the pose. And this is really rich if you want to, if you're a robot arm and you want to pick up the object, and knowing its pose is absolutely essential. And as all of you would know, all of these achievements in computer vision have been driven by three key innovations: better computers, better algorithms, generally deep neural networks, and lots of data to train from. But I'd argue that there are some other factors as well that have led to their massive progress. And I would say they include standard performance measures. So computer vision people compare very, very rigorously their performance with the performance of others using very standard measures. And robotics, we don't do this. And they use competitions, standard data, standard performance measures in competitions to harness the competitive juices of all of those young researchers. And the final factor, I think, very, very important, is compared to the robotics community, they were very early adopters of archive and what I call zero delay dissemination. So you've got a result, you write the paper, you put it on archive, and tomorrow people on the other side of the world are discussing your paper. You didn't have to go through reviewers, you didn't have to wait for a submission deadline, write it today and it's being read around the world tomorrow. And that has led to just an enormous acceleration of the rate at which it's possible to do this science. So I think we can't ignore the factors here. So if I stand back, and I'm director of a centre for robotic vision, and so there are people within my centre who would self-identify as computer vision people and others who'd self-identify as roboticists. Standing back and looking at it, you would say computer vision research is dominated by tables of bold numbers. And I think at one point I was probably a little skeptical about these tables of bold numbers. But I have to say, I think as a research methodology, rigorous comparison of your algorithm on standard data with standard metrics against everybody else has led to extraordinary progress. It's certainly driven the percentages in the tables up. Whether that translates to the real world is a different issue, but has led to massive acceleration in sophistication of algorithms. Whereas on the right-hand side, in robotics, we respect what we call experiments. Everybody knows you can't publish an ICRA paper or an IROS paper unless you've got an experiment in it. But I think we misuse the word experiment, and I want to dive into that a little bit. So I would argue computer vision research is driven by evaluation, a systematic assessment of how a system performs under well understood, agreed standard conditions. An experiment is supposed to be a procedure that you undertake to make a discovery or test a hypothesis. Now in robotics, when we conduct an experiment, I would ask you, what hypothesis is it that we're testing? And I don't think we do a very good job of posing hypotheses. And I could rather cynically say the hypothesis is simply that my robot will work. And what we don't say is that it maybe only work once. We took a video, the conditions weren't very clearly specified. I'd never be able to repeat that experiment. And that's not very satisfactory science. So I think we need to do a little bit better. And looking over the fence of what the computer vision people are doing with their evaluation-based methodology rather than experiment-based methodology, I think we could learn a trick from them. Evaluation allows you to say something crisp. My algorithm works X% better than your algorithm on this particular performance measure. So I think there's definitely stuff to learn there. So I believe the robotics community needs what the vision community has. Not just their algorithms, they've got fantastic algorithms and we can download their algorithms and put them on our robots. That's easy. I think it's a bit more than that. I think we need to take some of their approach to doing research. As I mentioned before, I'm director of the Centre for Robotic Vision. That's an ARC-funded Centre of Excellence, which finishes at the end of this month after a 7-year life. And we brought together research groups from around the country and from around the world who are interested in, if you like, reconnecting the fields of robotics and computer vision. These fields are both children of the artificial intelligence movement that kicked off in the late 1950s. But probably 2 decades ago, maybe even longer, vision people went one way and robotics people went a different way. And I actually think it's time that they have some conversations, some communications, some sharing, because I think they would each add value to the other. So some of the things that have happened in the centre over 7 years, this is some work from our colleagues in Adelaide on monocular depth estimation. So we have an input image at the top, monocular, and the middle image shows an estimated depth image. Trained from stereo, but it learns the mapping from monocular to depth. Here's some work that has happened in Adelaide, also on deep flow, visual odometry. It combines learning and visual geometry to come up with a very robust optical flow system, which we can use for visual odometry. And then we've combined that with very robust loop closure algorithms to have a system that's got a mixture of deep learning technology, where it's most appropriate, and visual geometry technology, where it's most appropriate. And this is a big debate, of course, at the moment, is how much physics and how much geometry that we've known it for hundreds of years, how much of that do we bake into the system, or should we just let the neural network figure that stuff out for itself? I think this is a really interesting debate at the moment. So this is a mixture of both, where I believe they're each used for the purpose where they have the most strength individually. This is some work from my colleagues here at QUT on semantic representation and sort of robust place recognition. So in the top right, you see two images. One's the front view out of a car window at night, and the right-hand image is looking out the back window of the car in the daytime. And we can be very, very sure that this is the same place. Radically different viewpoint, radically different time of day. So this leads to very robust localization based purely on vision. More work from colleagues here at QUT on quadric SLAM. So in moving beyond simple point features, because most of the objects in the world that we're interested in are three-dimensional, so we represent them with quadrics. We can tag them by their class, and then when we see them from different viewpoints, we can recognize that it is the same object and get around some of the sort of viewpoint variance problems that you get with typical point-based SLAM. Other work within the centre where we bring together robotics and vision. The first ones that I want to talk about is the Amazon Robotic Challenge, which very happily we won in 2017 against a very strong field. So for Amazon, the challenge that they have is they have robots that bring these product shelves to the dispatchers, and it's this lady's job is to reach into the shelf unit and pull out the item that the computer says she needs to pull out of the shelf and put it into the box that's going to go to the customer. So although Amazon have got cloud computing and robots to move the shelves around, they have this kind of like last meter problem where they have employed lots and lots of humans, and they want to automate that. So we first attempted this competition in 2016 with the Baxter robot. It was kind of clunky. We came 6th in the competition. The next year, we came back with a lot of ideas, a lot of learnings from the first round, and we created a brand new robot, and I'll show a video of that in a moment. Fairly low cost robot, probably the cheapest robot that was in the competition, and a pretty awesome vision system. So this is the robot. It's actually got 2 grippers. It's got a 2-finger gripper and it's got a vacuum gripper. And it uses the appropriate gripper for the object that it needs to pick up. And the essence of the job in the Amazon competition is to take items out of one tote and put them into the appropriate output tote. So this is the result of the segmentation and labeling that we developed. This was largely done by our colleagues in Adelaide using a system they developed called RefineNet. And you can see in the tote we have some pretty challenging objects. We have a bag of marbles, which are translucent and shiny. We have a wine glass, which is transparent. yet we do a reasonably good job of finding the contours and of labeling them. And once we have that information, we can plan grasp points and perhaps even the order in which we should be grasping things. We get some idea of which objects are on top of other objects. So together, the new robot and RefineNet gave us a winning edge in that competition. An interesting thing in the 2017 version of the Amazon Challenge is that there were a bunch of objects that would have been given to us just an hour before the competition started. So there was a big set of objects that we got long in advance and we could train on. There are other objects we got just in advance. So what you see here is two of the team members putting objects in front of the camera, setting them a few different viewpoints, and then we retrained or tweaked the network in the hour in order to allow it to recognize and deal with these objects. So we had to sort of pack a little GPU cluster with us at the competition. Reinforcement learning is kind of a very old idea that's become quite fashionable again, particularly deep reinforcement learning. And it's been shown recently to really to have some very, very impressive performance. This robot, if we watch it for long enough, will actually develop the ability to walk quite well. One of my students, Fanyi Zhang, is interested in applying deep reinforcement learning to the task of robotic reaching. So the idea is we want the robot to reach towards a blue cube. And in the right-hand picture, you can see Baxter's hand on top of a blue cube. So we trained the deep RL system completely in simulation. And Fanyi's work involved how do we do the sim to real transfer. So he was able to do it with maybe a few hundred unlabeled real-world images and a smaller number in the order of tens to 100 of labeled real-world images. And when we did that, we were able to transfer that skill from sim to real. And here's Fanyi sort of rearranging objects on the table. It's quite immune to clutter. And you can see wherever he puts the blue cube, the robot will move towards it. So the camera is in Baxter's other hand, the hand that's kind of up there like this. And the network that he created takes an image in and outputs the 7 joint velocities for Baxter's arm. One network, image in and joint velocities out, and it will just relentlessly reach towards a blue cube. It's just one skill, right? And it took a while to acquire that skill. But I think what we see the glimpse of is that we can train skills that's difficult to describe, train those, and then perhaps have ways to switch between the different visual skills or visual competencies. So another of my students, Doug Morrison, does a lot of work on grasping. And the traditional approach to grasping is you take a depth image, you propose a whole bunch of possible grasp positions and finger orientations, and then you go through some extensive ranking and choosing process, and then you execute the grasp that you figured was the best. What Doug came up with was a network, a generative network that takes a depth image and outputs for every single pixel in the scene how good a grasp point it is, and if you were to choose that point as the grasp point, how far apart should my fingers be and what should the orientation of my fingers be? And you can do this in 20 milliseconds. So what this allows us to do is to do grasping of dynamic scenes. Because computing a grasp now is so cheap, we can just do it in the servo loop, which opens up a whole lot of very new and interesting applications. Another robot vision system that I want to mention is Rangerbot, and this creation of my colleague at QUT, Matthew Dunbabin. It's an underwater robot, and some of you may well know this story of the crown of thorns starfish. I'll go through it very quickly. It's a starfish that eats coral. It's a native species, but it can turn a colorful coral reef into a coral desert. So Ames up in Townsville developed a toxin that could be injected by human divers into a starfish, but the coral reef is so massive, same land area as Italy, I'm told, it just doesn't scale to use human divers for this. So Matt proposed that we automate this with a robot, underwater robot and arm, injection system and cameras. So Matt, with another colleague, Faraz Dayoub, developed a deep net that can recognize the starfish, very distinctive texture. And once we had that, and that was trained on a lot of a relatively small amount of data that we had to gather. There are no data sets available of starfish images. We can connect that to the arm and then put the whole system together. And the robot flies along, it sees a starfish, it stops and hovers, it knows its altitude above the starfish, plans the robot manipulator path, and away we go. So interesting idea, the feasibility has been tested, but so far this has not gone into practice. And so this is Matt, and this is the latest generation underwater vehicle. We call this one Rangerbot. 2 cameras in the bottom, 2 cameras in the front, GPU on board. So it is a really powerful computer in a watertight housing with 6 propellers. It can do visual odometry, visual SLAM, surveys, can circumnavigate a reef. A lot of visual competence in this little machine. Another system that we developed a few years ago is a robot for broadacre weeding. So if you think about the revolution that's happened in food production on planet Earth, it's amazing. It's happened through genetics, better machines, herbicides and pesticides. It's what allows us to feed the 7 billion mouths on the planet today. And machines have grown in size, and that's really to improve the productivity of the person who drives the machine. And as roboticists, we'd ask the question, well, why are there people in the machines? Why make the machines so big and so brittle when perhaps you could use parallel processing? You have multiple small machines and have them work in parallel. So the work that I'm going to talk about really dates back to a linkage project we had with the company that became Swarm Farm, which is successful Queensland manufacturer of outdoor broadacre weeding robots. And so when we thought about the problem of making small, cheap robots that could navigate in a field, we wanted to do away with expensive RTK GPS receivers on each robot that would push the cost up. So we thought, well, cameras are cheap, they're built into phones and things like that. How far could we go just using vision? So this picture shows the team, a traditional big spray rig, and our little first generation vehicle. And the visual pipeline that we developed, in fact, our student Andrew English developed this. We take an image from a front-facing camera, we understood it, we stabilize it with respect to the horizon, and then we do a warp to an artificial overhead view looking down, so the crop rows are parallel, and that makes it then relatively easy to come up with robust algorithm for determining our offset with respect to the crop row. And that provides a steering signal into the robot. And this is an example of robot path overlaid on an aerial image of crop. We also did some work on obstacle detection. And the challenge here was we might want to find something that's lower than the nominal level of the crop. So that's Patrick on the right lying down. Here's the obstacle, but in terms of his height above ground, he's lower than the crop, which we don't mind driving through. And on the left-hand side, there's something that looks a lot like crop, but actually it's tall and we shouldn't drive into that thing. So these are kind of 2 interesting corner cases, and we developed an obstacle avoidance system that fused effectively visual surprise with 3-dimensional structure from stereo and gave us a very robust vision-based obstacle avoidance systems. That's Dave, who led the project, showing his confidence in a vision-based obstacle avoidance system. This is the second generation robot that we created here at QT. We call this Agbot 2. It's modular, it's got a lot of cameras underneath. It can return to its house, which is a shipping container, to recharge, it's all electric drive, and to replenish its supply of chemicals. When it's operating, its cameras look down at the ground, and in real time, we can segment the plants into crop or weed. We can classify the particular sort of weed, and then we can take an action, which could be anything from selective spraying, as you see here, through to localized mechanical tillage. So basically, we're going to mechanically chip the weeds out of the ground. So this is a way to dramatically reduce the amount of herbicide that needs to be applied to crops. So it's got an economic advantage as well as an environmental advantage. And we're actually just starting a new project at the moment looking at weeds in pastures. So these are weeds that are not good for cattle or reduce the productivity of cattle in a field. So moving from grown plants to the quality of pastures. The robot can also build huge photomosaics of the field, and we can sort of look at those holistically and get some idea about the patterns of weed growth within the field, which is a useful management tool. I'll talk very briefly about Harvey. It's another robot we developed here at QT, my colleague Chris Leonard. This is Harvey, and targeted at the problem of capsicum picking. And so here you see Harvey hand view of the capsicum. It's moving around to build a comprehensive colored point cloud and to remove the effect of occlusions that might be due to leaves growing around the fruit. Once we've got that, it's pretty easy to segment the fruit, plan a path, attach to it with a suction gripper, move in and sever the stalk. So with a single hand, we can grab the capsicum and cut the stalk. And humans do it typically with two hands, one to hold the fruit and one to snip the stalk with a pair of secateurs. But this robot's perhaps half the productivity of a human picker, but human pickers are hard to get. And our whole agricultural industry is really suffering from lack of labour. And that's a huge challenge for us as a country going forward. I'm going to skip this one and just talk a little bit about evaluating the performance of a robotic vision system. I think this is very important. So imagine you've got a robot and it's got a camera, vision algorithms on board, and you sit it on the ground and you push the go button and it goes and does a thing. And if you bring it back to the start point, put it as closely as you can to the start point and push the go button, it's very likely it will do a different thing. Because every time you take a picture, even of the same scene, the picture is slightly different due to pixel noise and whatever. If your initial condition is slightly off, then that will also cause the initial image to change. The initial image is different, the first motion it makes is different, that means the second image is even more different. So their paths will diverge over time. So that's not very satisfactory if every time I start my vision-enabled robot, it's an unrepeatable experiment. That doesn't help us at all. So thinking about how do we get the magic of what the computer vision people do, apply it to robots? And an image database doesn't work. What we need for robotics, the equivalent for robotics, is a simulation. So we have a couple of projects now within the centre where we're looking at building quite high quality simulated environments to test the absolute performance of a robotic vision system. So this particular challenge involves going around, a robot moving in a fixed trajectory through a complex environment, and the job is to recognize all of the objects that are in the scene. Right? Since we generated this sequence, we know the ground truth. So it's a way that we can compare algorithm A against algorithm B. Which one does the best job of finding all the objects? And then we can test their robustness with respect to variations in lighting level. So it's a way that we can start to say something profound, something metric about the performance of a robotic vision system. Now, the second challenge that we created, and the second challenge was launched this year, is we've now allowed the algorithm to be in the loop. So that the algorithm under test gets sensory information from this robot, from cameras and from LiDAR. It does the processing of that data, sends a move command to the robot moves and returns the next lot of sensory information to the algorithm under test. So this is really quite a sophisticated simulation environment and allows us again to compare robotic vision algorithm A against robotic vision algorithm B, or test the performance bounds of algorithm A by doing things like turning the lights up and down and so on, or changing the texture of the carpet. All these ways that we can test at what point, what are the limits of the performance of that algorithm. So we have a simulation version of this, and we also have the ability to load algorithms using Docker technology onto a robot in our lab. I'm going to skip really quickly. I'm going to skip through these slides because I'm kind of out of time. And I might just move here to some take-home thoughts, and I'm very happy to open it for questions. So first, I mentioned earlier that vision sort of accidentally transformed life on Earth. It made life on Earth much more interesting. And I can be kind of reductionist about things, and I think that we're proof that a robot with just one or two cameras could do all sorts of amazing things. We look at all the activities that human beings could do. I can't see any reason why a robot with two eyes can't do that same thing. Now, the challenge isn't the cameras, right? Cameras are pretty decent. The challenge is how do we process that visual information in a timely manner to allow this hypothetical robot to be as good as humans. Robotics has still got a long way to go. And I think really an essential part of their future is that they're able to see. And once they can, then they'll be able to help us in all sorts of sectors way beyond warehouses and manufacturing plants. And while deep learning has transformed robotic perception, it's a wave that's going to wash across robotics. It's already starting to wash across robotics. So perhaps in the future, we won't teach people about inverse kinematics and PID controllers. People will just train deep RL systems that will just do all of that stuff. It'll all be subsumed in a deep network. I think that potentially will happen within the next decade or two. Computer vision offers lots of things to the robotics community. It offers us really cool algorithms that we can just download and put onto our robot, but it's their methodology for doing research that actually I think is their secret sauce. And we should know that, understand that, and figure out how we can use that to drive robotics research forward at a faster rate. And finally, there's a bunch of tricks that biological vision systems use: active perception, attention, context. These are all tricks that we should be adopting in the perceptual systems that we build. I'll stop there and very happy to take questions. Thank you.
Okay, Peter, thank you so much. As always, very, very exciting content and a very exciting talk. Thank you so much for your time. We do have some questions online on Slack. I'll start with one from Yuxi, from Lyro.
Are they in the Q&A?
You mentioned a few things about benchmarking, and on the notes of benchmarking robotic experiments, the center, ACRV, I suppose, has done some work on that.
Correct.
So in your view, what are the lessons learned from those, and what are the ways forward in terms of getting more traction and take up from the broader robotics community in that direction of benchmarking? So that's one question there.
Yeah, getting uptake is hard. So just having a competition is not enough. Having a competition with a prize, sort of modest prize, is probably not enough either. It is about getting the word out. So certainly some of my colleagues, Nico Sunderhoff, Faraz Dayoub, and others, have spent a lot of time trying to get these two communities to talk. So we would run workshops at CVPRs, and we run workshops at Acre and RSS and so on, to try and raise the awareness of this kind of gap in the way we do research. And I think we are starting to get traction, but it's slow, and the events of this year have certainly not helped. I think we were just kind of getting some momentum and some traction, and then COVID hit, and that hasn't helped. But there has been engagement in the competition. The competition last year, which was the camera was on a fixed trajectory, and then this year the camera being an agent that you can control. The engineering of these challenges is very difficult. They're not cheap to put on. To create the complex three-dimensional environments challenging. To provide the compute is challenging. So I'm optimistic, and I would, with the resources we have at QUT now that the ACRV is ending, I would like to see this activity continue.
Okay. There's another question all the way from Texas, from Luis Santis. Thank you so much for still being connected. So he mentions that it's somewhat related to benchmarking, but I think he mentions that the skill set needed for robotics seems to be larger than that for the computer vision, and the minimum viable experiments for robotics seem to require more complex custom equipment, right? There's a lot of hardware involved and expensive parts. Yeah. Do you think the main reason for the gap on benchmarking, do you think that is the main reason for the gap on benchmarking between robotics and computer vision?
It's a very big part of it, and it's a really good question. I think, if you just try and, tap a computer vision person on the shoulder and say, hey, come over here, we've got lots of interesting problems. And I think they'll just look at you and say, that's just too hard a way to do research. To do, deep learning type vision research, all I need is my computer and a GPU cluster. No moving parts. It's really easy. And they probably look at their poor colleagues in robotics, pulling their hair out, trying to build a system. So it is, I think, a big barrier. And I think it's friction that slows us down as roboticists. So given that we could never convince vision people to come and play in robotics, what we've tried to do is to make the problem a bit more friendly to the vision people, abstract all of that stuff away. So if you like, in the second simulation challenge, the interface to the robot's really simple. You just give it a distance and a direction and just say move. So if you want to, you can do all the SLAM stuff yourself, but if you don't want to do the SLAM stuff, you can just give simple motion commands. Don't have to do any ROS or anything like that. Don't actually need a physical robot. Don't need space to run it. So really trying to remove every possible barrier to try and get the vision people to come over to our place and play.
Thank you, Peter. Another interesting question from Louis. He says that there seems to be more overlap between industry and robotics this decade than other times. It's unprecedented. Should academia go back to explore questions that are not necessarily commercializable? What's your view on that, please?
Absolutely, we should. I think that's the job of academia. If we stay in academia, then we should focus on problems that industry isn't doing. Our value is, I think, in training the people that will go and work for industry, be they undergraduates or be they graduate students going into industry. But I don't think it's healthy for academia if we just focus too much on industry problems. Being aware of what's an issue in industry is important. We need to pick our problems well and to be important problems and relevant problems. But no, I think there needs to be that separation.
Okay. I have a question, Peter. I've been meaning to ask you this for a long time, actually. Recently, a very famous individual stated that his autonomous cars would work with vision only and nothing else but vision.
Yes.
I know you're a big vision fan. What's your opinion on that? Do you agree or disagree? We're not talking about 100 years, right? We're talking short term where investors are waiting to see that as a product. Do you think vision can do it?
So this is Mr. Musk, right? All right. Look, part of me believes that it must be possible. I mean, humans are not great drivers, right? A million people a year get killed in car accidents, and the cars are wielded by humans. So you can't say humans are perfect drivers, but most of us do a lot of driving and do it pretty well, and we do that just using two eyes. I think the dominant sensing modality for autonomous cars today is LiDAR, and that's driven the cost of LiDARs down, which is a really good thing, actually. I mean, they've gone from the big Velodynes and the early Google vehicles, $70,000 down to thousands of dollars now. That's good. I don't think there are any vision-only solutions at this point. If they've augmented with anything, it would be radar. Right, so vision plus radar, I think, is a good solution, and I think it's got advantage in very adverse weather conditions. So with rain and fog, radar's going to give you, when vision's going to give you absolutely nothing. So while I believe passionately that it's possible to use vision only, we're not there yet. Maybe humans just don't have the risk appetite for a vision-only car that might make a mistake. We hold autonomous systems to a much higher level of account than we do humans.
Okay, thank you. So another question. You gave a review on the history of vision and advantages and disadvantages. So we have standard cameras, we have infrared, we have thermal cameras. More recently, we've been working with event-based cameras.
Yeah.
Do you have any secrets on what's next? What's the next type of camera that's going to be exciting for the research community?
I think I'm amazed that cameras, that there's still innovation in cameras, right? And so we're seeing very, very wide angle cameras, panoramic cameras. We see very low light cameras, cameras with ISO ratings of 500,000, a million, which you can see in almost complete darkness. I am very interested in event-based cameras. Probably initially a skeptic of event cameras, but looking at some of the algorithmic breakthroughs recently, I think they're amazing. For vehicles, their advantage are almost infinite dynamic range. That's very impressive. And the other one is that they're so fast, so motion blur is not a problem. So traditional cameras, you're moving fast in low light, you're just going to get stupid pictures. Event cameras seem to be able to give you pretty good pictures. And so people have done visual SLAM using event cameras, image reconstruction, visual optometry, all this stuff is happening now with event cameras. So and a number of manufacturers have kind of joined the bandwagon now, so they're starting to become mainstream. So I think that's probably, of all the cameras I know about, probably the one to watch out for, certainly for outdoor autonomous vehicles.
Okay. Thank you. So there's another question on Slack from Andrew MC. He asks, do you think NNs, neural networks, can be used to estimate calibration errors in multiple degree of freedom robotics?
Calibration errors in the robot or in the camera?
And neural networks can be used to estimate calibration errors in multiple degrees of freedom. Yeah, it's a good question. Andrew, if you're online, if you can clarify. Yeah, he's typing. Yeah, in robotics.
Okay. I think this whole notion of robot accuracy and calibration, I still feel is misguided. And it goes back to what I said sort of at the beginning of the talk. These are not calibrated, right? I mean, they're, if I want to pick something up, I use my eyes to make them near the thing I want to pick up. And so to me, requiring calibration, it's a crutch and we shouldn't need it. And so, I would just like to say we shouldn't be doing calibration at all. But maybe it's something a deep learning system can perhaps learn hand-eye coordination skills. And implicit in that hand-eye coordination skill is some notion of calibration. But I think it should be closed loop, not open loop.
Is the mic on? Yeah. Okay. Thank you, Peter. There are a few questions coming through. I think we're running out of time. We have time for one more question. Apparently, there's some in Zoom. Let me just check.
I can see two there.
Oh, yeah. If you can post on Slack. Okay. We're on Slack now. Yeah. So Ben has asked. Ben Tam? Yep. Oh, okay. So he asks, hi, Peter. You mentioned earlier in your presentation that although automation is possible in a lot of industries, there is low adoption. Why do you think this is? For example, the Crown of Thorns killing submarine. This is a workable and proven solution. However, it has not been implemented. Can you please comment on that?
Sure. So I think it comes down to the business side of robotics. So the Crown of Thorns submarine, there's no business model. Right? You can argue that it's a good thing to terminate these starfish because we like coral more than we like starfish, tough for the starfish. But what's the business model, right? And who should be paying for the upkeep of the Great Barrier Reef? We all love it, but it's the tragedy of the commons, right? No one's willing to pay for its upkeep. And so without that, there is no business model, therefore there is no submarine. And I think it's this issue really confronts us when we try and put robotics into any sector. why should a company tool up to build robots, take on all the development cost on the basis of possible future income without any sort of guarantee? And so although there's lots of areas where we think robots could work successfully, how do you bankroll the development of the robot to do that thing? Because robots are still, unfortunately, kind of still very single purpose. Although we've got lots of tools, technologies, algorithms, to build a robot to do a thing still takes, some good engineers, some number of years. It shouldn't be that way. I think it's less than it used to be, but it's still not as effortless as it should be. So that's a big problem for researchers and academics. You've got to make it easier to build good robots quickly. So someone's not going to take the financial risk on doing all that development work for an application where perhaps you're not sure on what the returns are. Now, you might be able to convince a VC to bankroll you for that period. And there's a lot of robot startups that are doing that. But I think it's because of the uncertainty in the eventual business model.
Okay, thank you. So one last question from Will Brown. He says, great talk. Where you mentioned that the brain doesn't have a geometric model of the world out there.
Yeah.
So is it plausible that it has an allocentric set of relationships and expectations that it uses? For example, pedestrians are on roads and not in trees.
Absolutely. I think that comes from our experience. So I'm not arguing that there's no representation. There absolutely is representation inside here, but it's not a metric representation. And it will be fascinating as we do more brain research and understand what the representations are, because I'd argue that they're powerful and robust representations compared to the ones we have now, which I think are rather fragile. So we look forward to people figuring out how the brain works. But this business about people on ground or people in trees, I think that comes from experience, and that's the sort of common sense, if you like, that autonomous systems need to have. What's the difference between a person, a bicycle, and a person wearing a T-shirt with a picture of a bicycle on it? We can reason over that. But a deep learning system may well be utterly confused by that. These are the challenges that
all right, I think we're going to wrap up here. Yeah. Mic is on. Yeah. I think we're going to wrap up here. Professor Peter Corke, thank you so much for your time. Thank you for supporting Acre 2020. I know you're a very busy person, so let's everybody thank the speaker. I know people cannot see, but just a virtual clap from everybody. Yeah, thank you so much. Any final comments, Peter, that you'd like to say before we move on, or?
Not at all. Just hope everyone has a successful conference, and it's great you've got attendees from Texas. Awesome.
All right. Thank you very much.